Thank you for coming at such an inconvenient time. This is Mireia González from FormalV Presentation. I'm the CTO of this company, also known as FormalV, which is based in Barcelona. And in our 5 to 6 years of history, our best contribution has been PCSS, which stands for Public Certification of a Specification and its Software. And that's what I'm going to speak about right now, because we believe this is the method to create the most reliable software. So, first of all, a bit of context. As many of you might know, these are crashes that have happened in the space tech industry. All of them cost millions of dollars, and in some cases, there were also human losses. And in all those cases, this was due to software bugs that could have been avoided. So, we're here to speak about how to avoid bugs in software. The usual answer to avoiding bugs is formal methods. But what are formal methods? So if we go to the NASA webpage, this is just a screenshot, we get something about rigorous mathematical techniques, but nothing very concrete. Same happens if we go to the Formal Methods Conference. They even admit that there is not a very rigorous definition of formal methods. So the issue here is that if we don't even know what formal methods are, we don't know what software bugs are, because if we don't have a notion of what correct means, we don't have a notion of what incorrect means. So the first thing we do is we restrict ourselves to a specific kind of formal method. This is formal method through proof assistance. Basically, a proof assistant is a program that allows you to write code and formal language, and this way you can write mathematical statements about your code and prove them inside the proof assistant. So you write mathematical proofs that have 100% certainty and are computer checked by the proof assistant. So in this setting, what does formal verification mean? So these are like the first items we would add to a definition. First of all, the software is based on a formal specification. A formal specification is a description of what the system should do, and it must be written in the formal language of the proof assistant. Then two, the formal specification is proven to follow all basic mathematical properties, like, for example, it is consistent, it has no internal contradictions, and it has no ambiguities, for example. Then three, the formal specification follows a computational limit in the sense that it is computable according to computability theory. And four, the software is mathematically proven to follow the formal specification. This is the key point. So this point means that we prove that the code follows what the formal specification says. Okay, so if we are in this setting, we have that the specification expresses what we want the system to do, and the software is proven to do so. So in this sense, we are safe. It means that if we have bugs, these bugs don't come from the software because it is proven to follow the specification. So the bugs are already in the specification. But we should ask ourselves, is this definition enough to avoid all bugs? So it's not, and for at least two reasons. First reason, we're leaving behind some specific kind of bugs, the bugs due to physical conditions. Let me put an example. Ariane 5, it crashed. And it was because the speed values were represented with 16-bit integers. Is this incorrect in a mathematical meaning of incorrect? No, it's not. It's okay. The problem is that the real physical values of speed overflowed 16-bit integers. So it crashed. And similarly, the Mars Climate Orbiter mixed kilometers and miles, which also resulted fatally. Then, we need a fifth element, which is that the formal specification takes into account the physical conditions. And we still run into problems. So the problems are that the specification expresses what we want the system to do, but it is in a formal language. So that's an issue, because usually when we imagine a system, we have a description in natural language. For example, I can imagine a function that sorts a list of numbers. But really, in the proof assistant, I write something more like the second part, the formal language part. And this is harder to check, and if you don't know the language, it's impossible to know if this is correct. If my description of what I want is more complex, like, for example, a C compiler, then the formal language description will take thousands of lines of formal language code that is very, very hard to assess. So here, as our CEO puts it, we are in the problem that what can be proven cannot be understood, and what can be understood cannot be proven. Meaning that what can be proven is written in a formal language, so we really don't understand it so much, and what can be understood is in our language, in natural language, and then cannot be proven. So what do? We need a translation. So we are adding more conditions to our definition that now will jump to public certification. Basically, we request 6, that the formal specification has an equivalent formulation or a translation, which is from the formal language to something closer to natural language. And this way we can guarantee that a spec that is accessible and close to natural language can transmit its correctness into the executable code. And I'll talk more about this later. We've reached this point. And the 7th condition is basically that all these items are publicly checkable, so that it can be checked by anyone who has enough knowledge about this formal language. And of course, it has been done at least once. Okay, so this is a recap of all of our conditions for what formal methods are to us, and then a software bug would be anything that violates this. So let me go into our method for implementing this PCSS, public certification. So basically, we have let's focus on the black box, the implementation or code. This is what any software system has. It has code, right? This is like the concrete steps that the computer must perform. Okay, in our case, we have an extra step, which is the extraction to the right. We need to do this because we are coding inside the proof assistant, which in our case is the Coq proof assistant. And proof assistants are not done to execute code, so they are very slow and non-efficient. We need to take the code out. We do that using a verified extraction mechanism. And right now we have 2 mechanisms. One to C, it's called CertiCoq, and it's developed by the team led by Andrew Appel. And another to OCaml, which is called MetaCoq, by the INRIA team led by Yannick Forster and Matthias Ozo. So these tools allow us to take the code from the proof assistant and verifiably take it out to executable code. Okay, but now let's focus on the verification part. So the dark blue box called formal specification. This says what the system should do. This is key. Of course, it says it in the formal language, in a mathematical language, which is non-accessible for everyone and is hard to understand. But still, it's much more abstract than the code, so it's a big improvement. And then the hard work is to prove that the code and the formal specification correspond to each other. That is done inside of the Coq proof assistant, and we have computer-checked proofs of this correspondence. So this is 100% guaranteed. Then the extra box in there, the FE5, this is the translation, or we call it technical specification, is a specification written in layers of language that are closer to natural language. And in this way, the user can go just to check the FB file and knows that the specification expressed in there in a language that they understand is what the code does. We take care of all the intermediate steps, that's for the experts, and the user only worries about something that they can understand. That's the key point. So, we have some projects, 3 industrial projects that are working, and PCSS projects don't need to be tested. They are correct by design. So if you test them, it's because you are looking for mistakes in FVFI, so in your expression of what the system should do, and not in the code. The code, you are sure it corresponds to what this document says. So just to give you insight, our projects, 3 projects were the following. First, the FV Time Manager. Basically, it's the first complete time manager system in UTC. It's based in the Blue Book protocol, which is the one used in most of the industry, including space industry. So the issue is that many other providers don't use UTC to the letter because they don't use leap seconds, which can be a very important thing to take into account in some critical systems. So this was the first thing. Then we have the SHA-256, which is one of the most widely used hash algorithms. So we have a working version of this algorithm that follows our method for PCSS. And we're now working on optimizing efficiency because it's not the most efficient. And in this process, we are working through multiple developments that enrich the proof assistant itself. Like, for example, extracting arrays from the Coq proof assistant to primitive arrays to the target language. This is joint work with the MetaCoq team. And finally, our third project was about computable laws. So a computable law is a law created with the aim to be the technical specification for designing software or automations of processes. So we are working particularly in the road transportation sector, where there are laws about regulating the hours of service of truck drivers. There are like European laws, the law in the US, and also other countries. And what we did was develop a global PCSS that works for all of these countries. The main challenge was that we had to take a law, a legal text, full of ambiguities, inconsistencies, and so on, and work on a mathematical framework that could serve as a base for this FI. This is the first publicly certified law, and it gives all guarantees to legal processes. So, as a conclusion and to recap, with this method, we believe we go beyond formal verification. So, a proof assistant really gives us a very strong point in verification, but we, with PCSS, want to go beyond, and the key to this is FVFI, so the translation into these levels of language closer to natural language. This allows to put the user in the position where they can control the system instead of being controlled by the system, and that's the point we wanted to make today. So thank you very much. We'll be tomorrow still in the booth 519 in this hall, so you are welcome to come. And I can answer any questions right now if you wish.